Hello, my friends. We're going to be solving trig equations. I decided to keep this all together in one video, but I'm still going to try to keep it short. We'll see how long it ends up going. When solving trig equations, you're going to use kind of the same solving techniques you've always used. You could do the basic solving, isolating the variable, taking the square root of both sides, factoring, and also a new one, rewriting using a single trig function. Let's get started. Alright, here we have 2 tan x minus square root of 3 equals tan x. In solving this, let's first think about it just like if we had a basic equation with only x's. Just like this, right? We would start by subtracting x over here. That would give us x equals, and adding the square root of 3 over there, square root of 3, and there we'd get our answer. We're going to do the same thing here, but instead of the x's, we're going to be using tangent x's. So what we're going to do is we're going to minus tan x from both sides, minus tan x over here. That's going to leave us with 2 tan x minus tan x, and then we're going to add this square root of 3 over to this side is going to equal the square root of 3. Now to solve for x here, think back to last unit. What we did was we drew these on a coordinate plane, and we know that tangent is opposite over hypotenuse. I'm going to put this over 1, so I know my opposite side is root 3 and my adjacent side is 1. Drawing these out, I see that I have a possibility in quadrant 1. My opposite, root 3 over adjacent, is 1. And I also have a possibility over here in quadrant 3. My opposite is negative root 3 over adjacent, negative 1. And negative root 3 over negative 1, of course, is the same as root 3 over 1. Now, I filled in these triangles, and these are in fact 30, 60, 90 triangles. And these are going to be 60-degree reference angles, which is equivalent to, right, pi over 3. So now let's find each of those angles. This one here is straight from the x-axis, so I know one of my solutions is going to be x equals pi over 3. For my other solution, I want this whole angle all the way to here, which would be pi plus this pi over 3, right? And if I change this to 3 pi over 3, add pi over 3 to that, I'm going to get another solution of 4 pi over 3. Let's try this one. Here we have 4 sine squared x plus 1 equals 4. Well, if I solve for sine squared x, I could subtract 1. That'll give me 3, and divide by 4. That'll leave me with sine squared x equals 3/4. And to solve for this sine x, since it's squared, let's square root both sides. Don't forget the plus or minus. That's going to leave us with sine x equals plus or minus the square root of 3 over 2. Now, going from here, let's put this on our coordinate plane. Since we're dealing with sine, we have our opposite side, our numerator, our hypotenuse, our denominator, and we have both these cases, the positive or the negative. Let's go ahead and start with the positive example. So our opposite side is positive root 3, our hypotenuse is 2. Drawing those, we're going to get 30, 60, 90 triangles in the positive y-axis quadrants 1 and 2. Now let's go ahead and let's take the negative example. That'll be negative root 3 as our opposite, and 2 is our hypotenuse. This time my opposite is negative, so I'm going to be in these quadrants 3 and 4 where the y value is negative, and my hypotenuse is 2, so again I have 30, 60, 90 triangles with 60 degree or pi over 3 radian as my reference angle. Now to get our final solutions, we just need to find each of these values. Starting with here, that's just pi over 3. Boom, there's one solution. Next solution, I need to find this over here. That's going to be pi minus this pi over 3. So that's 3 pi over 3 minus pi over 3, 2 pi over 3. Next, I'm going to have this 3 pi over 3 plus pi over 3 to give me my big angle, all of this right here. That's going to be 4 pi over 3. And finally, if I go all the way around to here, well, I know this angle right here is 2 pi or 6 pi over 3, and I need to subtract this whole angle from it, pi over 3. That's going to give me 5 pi over 3. Each of these angles just represent the the angle from the x-axis. Alright, here we have cosine x sine x equals 3 cosine x. Well, let's get our cosine x to the other side. That'll give us cosine x sine x minus 3 cosine x equals 0. These have a cosine x in common, so I could factor that out, leaving us with cosine x times sine x minus 3 equals 0. Since I've got two factors here, I could set each one equal to 0 and solve. Doing that, we're going to get cosine x equals 0 and sine x minus 3 equals 0, or sine x equals 3. Let's start by solving this cosine x equals 0. Cosine is adjacent 0 over hypotenuse 1. I know that's going to end up here at my hypothetical point, 0, 1, right? My x value is 0, my r value is 1, and also down here at my hypothetical point, 0, negative 1. So for this half of it, cosine x equals 0, I'm going to get solutions at x equals pi over 2 and 3 pi over 2. Going back over to my sine x equals 3. My opposite side is 3, my hypotenuse is 1. Oh, but here I should notice that my opposite side can never be bigger than my hypotenuse. The hypotenuse is always the biggest side. So this part of the equation has no solution. So my only solutions to this equation are going to be pi over 2 and 3 pi over 2. Now keep in mind all your other types of factoring that you can use. Just because we have trig functions doesn't mean they're not going to work for us. You can use any type of factoring tools you have. For example, this is a difference of squares. This could factor to sine x minus 1 and sine x plus 1. Over here we have a trinomial, right? Factors of 5 that add to 6. That's 5 and 1. This right here would factor to cosecant x plus 5 and cosecant x plus 1. Keep in mind all the factoring you've learned. All those methods will still work with trig functions. Okay, let's get into some rewriting using one trig function. Here we have 2 cosine squared x minus sine x minus 1 equals 0. Alright, right away I see I have cosine squared x and a sine squared x. These are two different trig functions. That's going to be difficult to deal with. The biggest tool we have here is going to be our Pythagorean. Because I see a cosine squared x, and I know that cosine squared x and sine squared x are both in the Pythagorean, let's go ahead and replace this using the Pythagorean. That's going to give us 2 times 1 minus sine squared x, replacing cosine, minus sine x minus 1. Let's rewrite this and put it in a form that we're familiar with. Distributing the 2, we'll get 2 minus 2 sine squared x minus sine x minus 1. Combining our like terms, we're going to be left with negative 2 sine squared x minus sine x plus 1. And this looks like something we can factor. Factoring this out, since I have a coefficient in front, I do negative 2 times 1. That's going to be negative 2. Factors of negative 2 that add to negative 1 are going to be negative 2 and 1. So I replace my middle term here with those two factors. I can proceed by grouping. Factoring out from each group, I'm going to get negative 2 sine x plus 1 sine x plus 1. Good, I have my sine x plus 1s in common. I can go ahead and factor that out. I'm going to get sine x plus 1 and negative 2 sine x plus 1 all equal 0. Let's go from there and split our factors up. That's going to give me sine x plus 1 equals 0, or sine x equals negative 1, and negative 2 sine x plus 1 equals 0, or sine x equals 1/2. If I take each of these, solving for each one by drawing my triangles out, I'm not going to do that for you here, you should get the solutions of pi over 6, 5 pi over 6, and 3 pi over 2. And that's just drawing out your triangles on coordinate planes and finding those angles. Alright, one more and we'll call it a day. Cosecant x minus cotangent x equals 1. This time we have different trig functions again, so we want to rewrite, but we don't have anything squared, so we can't yet use our Pythagorean identity. So, if we don't have anything squared, a great thing we could do here is, well, why don't we square it and see where we end up with? So let's first separate our trig functions, getting 1 on each side. If I add cotangent x to the right, I'm going to get cosecant x equals 1 plus cotangent x. From there, let's see what happens if we square both sides. That's going to give us cosecant x squared equals 1 plus 2 cotangent x plus cotangent squared x. All right, now we can use our Pythagorean. And let's go ahead and replace cosecant squared x using our Pythagorean identity. Doing that, we'll switch this cosecant squared x out with 1 plus cotangent squared x, and we'll get equals 1 plus 2 cotangent x plus cotangent squared x. Now, we've only got cotangents. Perfect. Let's rewrite this, set it equal to 0 so we can factor. That's going to give us 0 equals 2 cotangent x, because these cotangent squared x's canceled out, those 1's canceled out, so looks like we don't even need to factor here. All we need to do is divide by 2, and that's going to give us 0 equals cotangent x. Again, if we drew this out on our coordinate plane, we could find out where those values are going to lie. Cotangent is hypotenuse, sorry, not hypotenuse. It's going to be adjacent of 0 and opposite of 1. We know our opposite values of 1 are going to be here and here. And the adjacent values are 0, right? Because there's no x value of 0. So I know our solutions are going to be at x equals pi over 2 and 3 pi over 2. All right, if you have trouble drawing triangles and taking your values here and finding out where they lie on the coordinate plane, that's something you got to know. So this is a great lesson to refresh that skill, and that's going to be very important in solving these trig equations. Last thing, as a side note, I wanted to let you know we've been solving all of these on an interval going from 0 to 2 pi. So that's limiting us only from here all the way around from 0 to 2 pi. Trig equations actually have infinite numbers of solution. Remember, we're not bound by just one full circle of degrees, right? We could keep going and going and going and going. So keep that in mind. We're going to mostly be working from 0 to 2 pi, but there are also plenty more solutions that just kind of repeat themselves as they go around.